For decades, Uranus and Neptune were placed into a simple category called ice giants, and for a long time, that label seemed enough to explain them. Their cold blue appearance, distant orbits, and strange atmospheres painted the picture of worlds dominated by frozen materials like water, methane, and ammonia. But a new scientific study is now challenging that familiar idea. Researchers believe these planets may contain far more rocky material deep inside than scientists once assumed, suggesting their interiors could be much more complicated than the traditional ice giant description implies. They are not suddenly becoming rocky planets like Earth, but the findings raise important questions about how these planets formed, what materials built them, and whether we have misunderstood them for decades. In this video, we'll break down the discovery, explain why scientists are reconsidering these distant worlds, and explore what future missions may reveal about the true nature of Uranus and Neptune. For over 40 years, scientists and textbooks treated Uranus and Neptune as straightforward examples of ice giants. Their pale blue atmospheres and frozen environments made the label seem obvious. But the newest computer models are asking a much deeper question. What if the term ice giant only tells part of the story? Since no spacecraft has ever drilled beneath their thick atmospheres, scientists rely on advanced simulations to reconstruct what might exist inside these planets. Those simulations must match everything we can observe from afar, including mass, size, density, gravity, atmospheric chemistry, rotation, and magnetic fields. Instead of assuming one fixed structure, researchers tested thousands of possible combinations of hydrogen, helium, icy compounds, and rocky materials until the models behaved like the real planets we observe today. And surprisingly, many of the best matching results no longer resemble giant frozen worlds dominated by ice. Instead, they point toward interiors containing enormous amounts of rocky material, with some models suggesting that nearly 60% of the planet's heavy material could be rock by mass. That would place them closer in composition to dwarf planets, Kuiper belt objects, and even comets rather than simple water-rich worlds. Water, methane, and ammonia are still important ingredients, but they may no longer dominate the internal structure the way scientists once believed. This possible rocky interior also connects to another long-standing mystery. Uranus and Neptune appear similar in size, yet they behave very differently. Neptune releases much more internal heat into space, while Uranus barely emits any extra heat at all. Uranus is also tilted dramatically on its side, almost as if a massive collision struck it long ago and permanently changed its structure. These unusual differences have puzzled scientists for decades. If the two planets contain different ratios of rock, ice, and fluid layers deep inside, it could explain why their heat flows, magnetic fields, and internal dynamics behave so differently. The label ice giant may still technically apply, but this research suggests it functions more like a simplified category rather than a complete explanation of what truly exists beneath those blue cloud tops. Changing how scientists describe a planet also changes how they understand its history. Planetary labels are not just convenient names. They represent theories about where a world formed, what materials built it, and how it evolved over billions of years. If Uranus and Neptune are more rock-rich than previously believed, then the outer solar system may have formed from a far more chaotic mixture of materials than traditional models suggested. For years, the standard explanation was relatively simple. Close to the young sun, temperatures were so extreme that only rock and metal could survive, leading to the formation of planets like Mercury, Venus, Earth, and Mars. Farther away, where temperatures dropped low enough for volatile compounds to freeze, giant icy cores supposedly formed Uranus and Neptune, while Jupiter and Saturn captured enormous amounts of hydrogen and helium gas. But if rocky material dominates large portions of Uranus and Neptune, then the early outer solar system may have been filled with a chaotic blend of rocky debris, icy planetesimals, and mixed materials feeding the growth of these worlds all at once. The implications extend even deeper when scientists examine the planet's magnetic fields. Unlike Earth's relatively organized magnetic field generated by its metallic core, Uranus and Neptune possess wildly tilted and off-center magnetic fields that behave in extremely unusual ways. For years, researchers suspected their internal dynamos existed inside strange fluid shells rather than neat central cores. If these planets truly contain mixtures of conductive fluids, compressed rocky material, and volatile compounds under crushing pressure, then those bizarre magnetic fields suddenly make more sense. Their interiors may be layered, unstable, and constantly shifting rather than smoothly organized. This idea could also help explain why Neptune releases so much heat while Uranus appears strangely inactive. Some scientists believe Uranus may have experienced a catastrophic impact early in its history that disrupted its interior and trapped heat beneath layered boundaries. If the planets formed differently or contained different internal compositions, then their entire evolutionary histories may also be very different despite their similar appearance from space. These discoveries do not only affect our understanding of the solar system, they also influence how scientists study exoplanets orbiting distant stars. Around other suns, astronomers frequently discover worlds similar in size to Neptune and automatically classify them as mini-Neptunes or ice-rich planets based mostly on mass and radius. But if Uranus and Neptune themselves are not simple ice-dominated worlds, then many distant exoplanets may also be far more complicated than current categories suggest. Some may contain huge amounts of rock, others may be dominated by deep oceans or thick gas layers, and many could possess complex stratified interiors that current telescopes cannot yet fully detect. The deeper lesson is that planetary categories are useful shortcuts, but nature itself is often far messier than the labels scientists create. Uranus and Neptune may still belong to the ice giant family, but the new research suggests those worlds sit in a blurred boundary between rocky planets, icy bodies, and gas-dominated giants. One of the most important conclusions from this study is that scientists urgently need better data. Right now, nearly everything we know about Uranus and Neptune comes from telescope observations, mathematical modeling, and one historic mission. NASA's Voyager 2 spacecraft remains the only probe ever to visit either planet, flying past Uranus in 1986 and Neptune in 1989. Those brief encounters transformed our understanding of the outer solar system, but they were still only short flybys. They could not provide the detailed long-term measurements needed to fully map the planet's interiors or understand how their internal systems evolve over time. A dedicated mission to either planet could completely change the picture. An orbiter around Uranus or Neptune could measure gravity, magnetic fields, atmospheric structure, internal heat flow, and seasonal changes with far greater precision than ever before. Those measurements would allow scientists to test whether these planets are dominated by icy material, rocky interiors, or complex layered structures hidden deep below the atmosphere. An atmospheric probe descending into the clouds would also provide critical information. Such a probe could directly measure gases, chemical abundances, temperatures, and atmospheric composition while traveling through the upper layers. Although it would not reach the deep interior, those measurements would still provide important clues about the materials that originally formed the planet. Combined with gravity and magnetic field measurements from an orbiter, scientists could dramatically reduce the uncertainty surrounding current models. The study also revives major questions about planetary migration. Some theories suggest Uranus and Neptune may not have formed in their current positions at all. Instead, they may have originated closer to the Sun before migrating outward during the chaotic rearrangement of the giant planets early in solar system history. If that scenario is true, then their rocky composition could preserve evidence of a completely different formation environment than the distant region where they now orbit. For now, scientists will likely continue using the term ice giant because it remains a practical way to distinguish Uranus and Neptune from rocky planets and gas giants. However, this research suggests the label may require much more careful explanation moving forward. These planets are not simple frozen spheres drifting through space. They may contain rocky regions, volatile compounds, deep conductive oceans, exotic fluid layers, and materials compressed under pressures far beyond anything found on Earth. Most importantly, this study does not instantly rewrite planetary science textbooks. Instead, it sharpens the biggest unanswered questions. How much rock exists inside Uranus and Neptune? Are their interiors smoothly mixed or divided into separate layers? Did the two planets form from similar materials or completely different environments? Why does Neptune emit so much more heat than Uranus? And how closely do these worlds resemble the countless Neptune-sized exoplanets now being discovered throughout the galaxy? Until a new mission finally returns to the outer solar system, many of these mysteries will remain unsolved. But that uncertainty is exactly why the study matters so much. Even after centuries of observation, Uranus and Neptune still hide some of the most fundamental secrets in planetary science. Their blue atmospheres and distant orbits may feel familiar, yet deep beneath those clouds could exist some of the strangest and least understood environments anywhere in the solar system. Uranus and Neptune are not officially being reclassified today, but this new research suggests they may be far more rocky and structurally complex than the traditional ice giant label implies. For now, they remain two distant worlds that humanity has only briefly visited, and whose true interiors may still hold secrets capable of reshaping how we understand planetary formation itself.